Hey everybody, welcome back to chemistry. And now we're going into a particular kind of problem called a heat transfer problem. And so in a heat transfer problem, usually it starts out by having some hot object, maybe a piece of metal. And what you're going to do is you're going to take that hot object and add it to a relatively cool object, say water. What happens then is that if you give it enough time, the hot object will become cooler and the cool object will become warmer until they've reached thermal equilibrium. When that happens, then the hot and the cool object will then be at the same temperature. After that, in the problem, you may have to do some kind of calculation. You may have to figure out, for example, what the final temperature of the metal and the water is. So to show you how to solve these problems, let me go over to the computer here. So here we have a picture here, which I'm sort of highlighting there. And so again, the picture sort of describes a situation where maybe we have this hot object here. I'm drawing a box around it. Think of it as a piece of metal, for example. And then it's surrounded by relatively cool matter, which is water here. So that is the initial setup of the experiment. But given enough time, what will happen is that you'll have heat leave the hot object and go into the relatively cool water, and then finally you'll be in this situation here. And in this situation, what's going on is that the metal and the water have achieved the same temperature. Okay, so how do you solve problems like this? Well, one thing that is very helpful is, if you can, being able to designate what a system is and what a surroundings is. So let me talk a little bit about that. So we can imagine here the hot piece of metal as being the system here. And so it's indicated in this picture here that the metal is the system. And then what we can imagine is that the relatively cool water is the surroundings. And so if we do that, we can solve the problem by understanding that any heat leaving the system must be gained by the surroundings. And so we can write an equation for that, which I have here, is that again, any heat leaving the system will be gained by the surroundings. Okay, and so this is often written as Q of system is equal to negative Q of surroundings. Now you might wonder, why is it Q of system and negative Q of surroundings and not Q of system is equal to positive Q of surroundings? And the reason is this: you have to sort of, in the equation, describe the direction of the heat transfer. And so if you have heat that is leaving the metal and that is positive, then any heat being gained by the water is going to be negative. So we do have to write Q of system is equal to negative Q of surroundings. Okay, so you start out with that, and then what you can do is you can sort of modify the equation to solve the problem if you wanted to. And so, for example, in a lot of heat transfer problems, the surroundings will be water. And if so, then what you can say is that the Q of the system is equal to the negative Q of the water instead of the negative Q of surroundings, and that's perfectly fine. And then also what you'll find is, in a lot of heat transfer problems, you're going to be dealing with a system that is a piece of metal. And so all I'm doing there is substituting Q of metal for the Q of the system. And so what we can say here is that here the Q of the metal is equal to the negative Q of the water, or we can just sort of use letters here. The Q of M is equal to negative Q of W. Now, you might remember what the formula for the specific heat capacity for a piece of matter is. And so the specific heat capacity is the letter C, so I'm highlighting that there. And you remember that the specific heat capacity is equal to Q, which is the heat, divided by the mass times the change of temperature of the matter. So what we can do is we can rearrange that formula and solve for Q, which we have done. Q is equal to C times M times delta T. And then what we can do is we can substitute in C times M times delta T for Q of the system and Q of the surroundings, or more specifically, for Q of the metal and Q of the water. So I've done that here. So before, when we had Q of the system and negative Q of the surroundings, after substitution, we have C times M times delta T of the system, and then we have negative C times M times delta T of the surroundings. Now, if we're looking specifically at, say, a metal system and water surroundings, same deal. What you can say now is that the system is the metal, so it's going to be the C times the M times the delta T of the metal. It's going to be equal to the negative, the C times the M times the delta T of the water. Okay, so let's go ahead and try a certain problem here. So I have this problem here. It says a 360-gram piece of iron is dropped in 500 milliliters of water at 24 degrees Celsius in a styrofoam cup calorimeter. The final temperature of the water was measured as 42.7 degrees Celsius. Calculate the initial temperature of the piece of iron. And then we have some additional information there that might help us solve the problem. We're given the specific heat of iron, and we're given the specific heat of water, and we're also assuming that the density of the water is 1 gram per mil. Okay, so let me go to the board and solve this problem. Okay, so what usually helps me out is maybe drawing a picture of what is going on, and then I'll write out some equation that could help us. All right, so here we have some kind of container. They're saying in this problem it's a coffee cup calorimeter, but that's not really so important. And so here what we imagine here is that I guess there is some water in it. And so let me just note here that there are 500 milliliters of water. Okay. And now also we know what the specific heat of the water is, and so let me indicate that here. So C is 4.184 joules per gram degrees Celsius. Now we have some additional information about the water. We have an initial temperature for the water, and we have a final temperature of the water. So the initial temperature of the water is going to be what? 24.0 degrees Celsius. And the final temperature of the water is going to be 42.7 degrees Celsius. Okay. Now, to that water, what we'll do is we'll have a chunk of hot metal in there. At least it'll start out as hot. And so this is the metal here. Let me just indicate here that this is the water out here. Okay, so do we have some initial information about the metal? And we do. So let me write this information here. Get it. Okay. And so the metal, it looks like we're given the mass. It's 360.0 grams. Are we giving the specific heat of the metal? Yes, its metal is iron, and so the specific heat is C is equal to 0.451 joules over gram degrees Celsius. Now, are we given any kind of temperature information about the metal? We are not given the initial temperature in the metal. In fact, that is what we're trying to find. So let me just indicate that the initial temperature of the metal, again, is because we're trying to find it, I'll call it X. So what is the final temperature of the metal? Do we know that? And the answer is we do know what the final temperature of the metal is. And so the final temperature of the metal should be exactly the same as the final temperature of the water, because the metal and the water, given enough time, will come to thermal equilibrium. And so again, the final temperature of the metal should be the same as the final temperature of the water, so it should be 42.7 degrees Celsius. Okay. Now let's think about how we go about solving this problem. So what we're going to do is we're going to make this very important assumption, that any heat lost by the hot metal will be gained by the water. All right? So what we can do is sort of generalize this a little bit more. Let's say the metal is the system. So this is the system. And let's say the water is the surroundings. So now we can sort of generally say that any heat lost by the system will be gained by the surroundings. Okay, so let me write out an equation for that. So here we have Q of the system is equal to negative Q of the surroundings. All right, now what you can see is that the system is the metal and that the surroundings is the water. So what we're going to do is I'm going to rewrite this. I'm going to say Q of the metal, which is M, is equal to negative Q of the water, which is W. Okay. Now, at this point, it'd be good if we could substitute in for Q. The formula of that includes specific heat. So let me go ahead and write that out. So you might recall that the specific heat of a substance is equal to Q over M times delta T. So can you solve this for Q? I'll go ahead and do that. Q is equal to C times M times delta T here. So now we can substitute for Q, C times M times delta T. So let me do that here. So for Q, we have C times M. I'm going to leave out the times sign, times delta T. And so this will be for the metal. And then we substitute that for the water side. So it's negative C times M times delta T for the water. Okay. Now, let's go ahead and substitute in some values into this equation that we have here. And then I think it will become more clear how do we solve the problem. And so what I'm going to do is I'm going to focus in right now on the left side of the equation, which is for the metal. Okay, so are we given the specific heat of the metal? And the answer is yes. The specific heat of the metal is here is 0.451 joules per grams degree Celsius. So let me write that here, 0.451 joules per gram degree Celsius. And then what I'm going to do is I'm going to multiply that by the mass of the metal. Are we given that? Yes, it's 36.0 grams. So let me write that here, 360.0 grams. And so we have that here. All right. Now, the temperature change of the metal. Okay, that's a little bit trickier. So what we have here is you'll have to remember the temperature change is going to be equal to the final temperature minus the initial temperature. And so this applies for the metal here we're talking about, so I'm adding M's here. Okay, so let's figure out what the temperature change of the metal is given the information that we have. So we have the final temperature of the metal. It's 42.7 degrees Celsius. But do we have the initial temperature of the metal? No, that is what we're trying to find. That's the X. So I'm going to put an X there. All right, so let me go ahead and throw that in to the temperature of the metal. It's 42.7 degrees Celsius minus X. All right, so now this is the metal side of the equation. So let me just indicate that here. So this is the metal side of the equation. So this is metal. Okay. Now, what we have to do is make this equal to the water side of the equation. So let me write that out. So the first thing you have to remind yourself of is that there's a negative here. And now what we need to do is we need to get the specific heat of the water. That is 4.184 joules per gram degree Celsius. And so let me write that here, 4.184 joules per gram degree Celsius. And then what we're going to do is multiply that by the mass of the water. Is that given to us? Yes. We're told the volume of the water is 500 milliliters. So the density of water is 1 gram per mil, and so we should have 500 grams of water. So it's 500.0 grams of water. Okay, now we have to figure out the temperature change of the water. So let's go ahead and work that out. So the temperature change of the water is delta T is going to be equal to the final temperature of the water minus the initial temperature of the water. And so just to indicate that this is water, I'm going to put W's here. So what is the final temperature of the water? It is 42.7 degrees Celsius. What is the initial temperature of the water? It is 24.0 degrees Celsius. And so what it's going to be is it's going to be 18.7 degrees Celsius. All right. And so here what we do is we write in here 18.7 degrees Celsius. Okay. So let me just clear this out a little bit. So what you can sort of see here is that we sort of have an algebra problem here. Okay, so what we have to do is, let me just point out what we're going to have to end up doing, is what we're going to have to end up solving for this x here. So let's go ahead and carefully do that. Okay, so here we go. So let's go to the metal side here. and let me just indicate that this is the water side. Okay, so the metal side, let us go ahead and multiply these two numbers together. So I did this earlier, and what I got was 162.36. Now, what are the units? And so here what you can see is that grams cancels out, right? So we should have joules per degree Celsius. And so what we're going to do is we're going to have to multiply that by 42.7 degrees Celsius minus x. Okay. Now let's go to the other side of the equation here. So what I'm going to do is I'm going to multiply this number by this number by this number and keep the negative sign here. And so when I did that, what I got was 39120.4. So what are the units here? And I think what you can see is grams cancels out, degrees Celsius cancels out, and then we're left with joules, like that. Okay. Now let's keep going here. Let's go back to the metal side of the equation. What we have to do is we have to multiply 162.36 by 42.7 and then also by negative x. So we distribute 162.36 with 42.7 and negative x. So what I got is 162.36 times 42.7. I got 6932.772. Okay, and so the units here, I get joules, and then I have minus, and then I need to multiply this number times x. 162.36 joules per degree Celsius x is equal to negative 39120.4 joules. Okay, now what I want to next do is I want to have this x by itself. And so we can leave it on the left side of the equation and keep it negative. What that means is that we have to move the 6932.772 joules from the left side of the equation to the right side of the equation. So over here it's positive. So how do we get rid of it? We get rid of it by subtracting here that number, negative 6932.772 joules. And so we subtract over here the same value, 6932.772 joules. And so after I do that, these two numbers, they neutralize each other, if you will. And so you get negative 162.36 joules over degrees Celsius x. And then if you add these two negative numbers together, what I got was negative 46053.172 joules. Okay, so the final step is we're going to have to divide both sides by negative 162.36 joules degrees Celsius, like this. Negative 162.36 joules degrees Celsius. And so after we do that, we get x. So the number you get rounded to the correct number of significant figures should be 284. So how about the units? Well, what you can see is that here, joules in the numerator cancels out with joules in the denominator here. We have degrees Celsius in the denominator of a fraction that's in the denominator of another fraction. So that throws it into the numerator. And so that should be the correct answer. Now, one thing you can do in the future if you want to is when you solve these problems, you can maybe, as you're solving the problem, maybe leaving out the units. That might make it a little bit less complicated. But then you sort of have to be a little bit more careful when you're solving the problem, because a lot of times if you do leave in units as you're solving the problem, you'll spot an error. So just keep that in mind. That may be a quicker way to solve the problem. So thank you for listening, and we'll see you next time.